The recent release of two new images of the interstellar object 3I/Atlas on November 5, 2025, has generated significant scientific interest because of what they fail to show as much as what they reveal. These images, captured by some of the same powerful ground-based telescopes that have been tracking the object for months, depict 3I/Atlas as a compact, nearly point-like source of light. What stands out is the absence of a defined or extensive cometary tail. Even the coma, the diffuse cloud surrounding the nucleus of an active comet, appears unusually subdued. When these new images are compared to the earlier observations taken by the Hubble Space Telescope on July 21, 2025, the morphology of 3I/Atlas appears remarkably similar, despite the object having passed near perihelion during the intervening time. This stability is unexpected because perihelion is typically when comets experience their strongest outgassing, heating, and mass loss. The persistence of such a compact coma before and after perihelion suggests a physical behavior that diverges from what astronomers expect from ordinary cometary bodies. This puzzling appearance becomes even more intriguing when considered alongside NASA's Jet Propulsion Laboratory's report of a measurable non-gravitational acceleration acting on 3I/Atlas. According to JPL's analysis, the object exhibits a transverse acceleration of approximately 3.7 times 10 astronomical units per day squared when normalized to a heliocentric distance of $1 Australian. Such a non-gravitational component typically arises from anisotropic outgassing, the process where sublimating gases escape more strongly from one side of the nucleus than another, pushing the comet in the opposite direction. This phenomenon has been well documented in many solar system comets, especially when they approach the Sun. However, in this case, the level of acceleration is quite substantial, large enough that it should correspond to a significant release of mass from the object's surface. The expectation, based on long-established cometary physics, is that such vigorous outgassing should manifest visibly as an extended coma and a distinct tail composed of dust and ionized gases, both of which are pushed away from the Sun by radiation pressure and the solar wind. Motivated by these reported non-gravitational forces, I performed a momentum conservation analysis, following the same principles commonly applied to active comets. This analysis led me to an estimate that the mass fraction lost by 3I/Atlas during its perihelion passage must exceed 13%. Losing more than 13% of its mass is not a trivial event. For a typical cometary body, it would represent a dramatic episode of activity. If such a mass loss had actually occurred in the form of dust and gas expelled from the surface, the visible consequences would be unmistakable. We would expect to see a bright, extended coma surrounding the nucleus, potentially tens of thousands of kilometers across, as well as a long tail stretching away from the Sun, shaped by the interplay between radiation pressure, the solar wind, and the comet's trajectory. These features are not subtle. Astronomers routinely observe such structures even in small or moderately active solar system comets. Yet the new observations show no such tail, and the coma remains compact and faint. This discrepancy creates a tension between the theoretical implications of the measured acceleration and the visual reality captured by telescopes. To appreciate how unusual this is, it helps to compare 3I/Atlas with a familiar example. 2 days before the November 5 images of 3I/Atlas were taken, the same telescope network observed Comet Lemon, a typical solar system comet that also appeared in the same region of the sky. In those images, Comet Lemon displays precisely the kind of morphology we expect from a comet that is undergoing normal outgassing: a bright head and a clear, extended tail that points away from the Sun. The tail is shaped by dust and ions streaming off the nucleus and interacting with the solar wind. Even with modest activity, this tail structure stands out distinctly. The contrast between the vivid tail of Comet Lemon and the compact, tail-less appearance of 3I/Atlas highlights just how anomalous the interstellar visitor's behavior truly is. This raises a series of deeper questions about the physical composition and behavior of 3I/Atlas. If it is indeed losing mass rapidly enough to produce the measured non-gravitational acceleration, why does that lost material fail to form the expected coma and tail? One possibility is that the mass loss is dominated by extremely fine dust grains or gas molecules that do not scatter light efficiently enough to be seen. However, radiation pressure affects small particles very strongly, often enhancing the visibility of fine dust rather than diminishing it. Another possibility is that the outgassing is occurring in such an unusual geometric pattern, perhaps highly collimated jets directed in a way that minimizes visible coma formation, that the released material remains undetectable. But such an explanation would require finely tuned jet behavior, something not commonly observed in natural comet nuclei. Alternatively, it may be that 3I/Atlas is composed of materials that sublimate or fracture in ways very different from solar system comets. Interstellar objects can form under a wide variety of physical conditions, influenced by the chemical, thermal, and radiative environments of their home systems. Their compositions might include exotic ices, refractory compounds, or even low-density aggregates that do not behave like the water-dominated comets we observe locally. If the mass loss is dominated by volatile gases with little dust content, the gas might disperse rapidly into space without forming an observable coma. Yet even gas-dominated comets produce detectable ion tails, so the complete lack of visible structure remains puzzling. Another angle to consider is whether the observed acceleration could have a non-cometary origin. If 3I/Atlas is not losing mass in the way typical comets do, perhaps the force acting on it arises from another physical mechanism. Some models have proposed that interstellar objects might be subject to unusual radiation-driven forces if they possess high area-to-mass ratios, such as very low-density structures or flattened geometries. In such cases, the object would respond to sunlight more strongly than a compact, dense nucleus would. This would not require mass loss at all. While speculative, these possibilities have been explored in the context of previous interstellar objects like 1I/Oumuamua, which similarly exhibited non-gravitational acceleration without showing a typical comet tail. The parallels between 1I/Oumuamua and 3I/Atlas raise the question of whether interstellar objects may commonly differ in fundamental ways from the comets in our solar system. Regardless of the underlying cause, the mismatch between predicted mass loss behavior and observed morphology means that 3I/Atlas does not conform to the standard cometary model. It challenges the assumptions that astronomers use to infer physical properties from dynamical measurements. Its behavior suggests that interstellar objects may represent a broader population of bodies with diverse physical characteristics, shaped by the environments of their home systems and altered by long journeys through interstellar space. Every new interstellar visitor gives us only a brief observational window, but during that time it forces astronomers to revisit long-standing theories about cometary physics, small body evolution, and the influence of non-gravitational forces. The November 5th observations offer an important data point in this ongoing debate. If 3I/Atlas truly shed more than 13% of its mass, yet remains visually compact with no tail, then either our understanding of mass loss dynamics is incomplete, our assumptions about its composition are incorrect, or the observed acceleration must be attributed to a mechanism other than outgassing. Each possibility carries significant implications for the study of interstellar bodies. Further observations, especially spectroscopic measurements that could detect faint gas emissions, will be crucial in resolving this mystery. As the object recedes from the sun and fades, researchers will continue to track its trajectory, refine the acceleration models, and compare them with the visible morphology. Whether the explanation lies in exotic physics, unusual composition, or simply an incomplete understanding of how interstellar objects behave, 3I/Atlas stands as another reminder that the universe still holds many surprises.